Okay, guys, welcome to section 5.4 and 5.5 and 6.4, which are inverse functions of trig functions, inverse trig functions to be exact. Guys, I'm gonna be honest with you. This is not truly our definition of trig function. If you remember, not trig function, of inverse function. In order, if you recall back in chapter 2, we said in order for a function to have an inverse, okay, in order for it to have an inverse, it must be 1-to-1, i.e., that means it must pass the horizontal line test. And what the horizontal line test does is make sure that for every output, there is exactly only one input that'll give you that output. So for example, let's look at this function. It's not a trig function, but it's a guy you've seen before, x squared. Okay, so here's x squared. Now if you look at the horizontal line test, let's get some different colors going here. Here's a horizontal line for you. Okay, now if I sweep this up, if you notice, when it hits the line, everywhere it hits it in 2 spots. That means for this particular value of y, okay, there are 2 x's that'll give you that same value. For example, if you plug in -2, right, you get 4. Well, if it was 1-to-1, when I plugged in 2, I should get something totally different. But I actually end up getting 4. So 4 is mated up with 2 different guys, okay? So therefore, this guy is not going to have a definable inverse, okay? And here's your proof. Here's your proof, okay? Remember how we found an inverse before? We had changed the f of x into y. And then we would flip-flop the x and the y and solve for x first. So you get square root of y, that's plus or minus x, right? And then this means that this is your inverse. F is the inverse of plus or minus the square root of y, but square root of x. But guys, it can't be 2 functions in one. That's piecewise. It's piecewise. So therefore, he doesn't have a definable inverse. Okay. So let's take a look at our trig functions. What is this guy? Correct. You said sine, right? What is this guy? That guy is cosine. Okay, note, none of these guys pass the horizontal line test either. So they don't have definable inverses. Okay, look at tangent. All right, these are asymptotes, by the way. He doesn't pass the horizontal line test. Notice he gets cut in 3 different places. Okay, so what is the deal? Why are we even taking time to even look at this? Well, what we're going to do is we're going to fabricate a trig function. Okay, let's just look at sine for right now. That has an inverse. If you look at sine inverse, right? What's the domain on sine? Well, domain is all real numbers. The range is -1 to 1. Okay, if he has a true inverse, then what should happen is that for the inverse function, and we'll talk about what we're going to call that in a second, his domain, the domain of the inverse, should be the range of the original function. So it should be -1 to 1. But here's a problem. Here's sine. And we'll call this 0 instead of that 0. So sine does one of these guys. Boom. It goes back forever, right? So here's the problem. We need, for every output on the original function, for this -1 to 1 should be the domain of the other function. So our other trig function should only have a domain from -1 to 1. But remember, it must be 1 to 1. So here's what we're going to do. If you trace forwards, all these numbers from -1 to 1 will cover here. But if I cross over, then it won't pass the horizontal line test. So I just want from here to here. Okay, when is sine at its highest point? Well, that's pi over 2. Likewise, but how do I catch the other numbers in the range down here in the x? Well, what I do is I trace backwards. So what we end up doing is, and which this happens at -pi over 2. What we end up doing is making a new trig function that happens to be the inverse of sine. And what do we call this trig function? We call this trig function arc sine. Okay, or sometimes denoted as sine inverse, okay, of the answer. Okay, so here's something I always want to keep in mind. The answer. So check this out. We plugged in for the original function. We plugged in a radian or an angle, and what we got out was a number. Well, here we're plugging in a number. So what should we get out? An angle. Because it's an inverse function, right? We fabricated. But here's the difference. The range, and this is the big piece of the puzzle, the range only goes from here to here. So it'll be negative pi over 2 to pi over 2. That's what I mean by it's not a true inverse function, because this domain and this range should match, but they don't. Okay? They don't. So note that this is all you really need to know, that it has a this additional idea to it. All right, let's do a couple. Once we do a couple, you'll get the hang of it. It's really not that bad of an idea. Okay, so let's erase this. Here we go. So let's say I want you to find the arc sine of negative 1/2. So first things first, in your mind, once again, the negative 1/2 is the measure. This is always going to be equal to an angle. We're looking for the angle theta. So how do we find the angle theta? Well, first things first, we have to translate in our mind what this means. Because remember, arc sine is just an angle. So what is this saying to us? Well, this is kind of like solving an equation. Sine of what angle is negative 1/2? But also we have that added restriction we just talked about. That theta must be in between pi over 2 and negative pi over 2. So let me ask you a question. Sine of theta is negative where? Correct. 3 and 4. Negative pi over 2 to pi over 2, well, where is that? Well, that's in 1 and 4. So where are we living? 4. All right, so let's draw me a handy-dandy floating triangle here. And let's hopefully I can get some good stuff going. So here we go. Here I am in 4. And here's the angle theta. So who do we know has a y value of negative 1/2? I don't know who that guy is that has a y value of negative 1/2 and x value of negative root 3 over 2. Well, I could tell you I am quite confident that this guy is the guy that we would normally call, if we went around from here to here, we normally call this guy 11 pi over 6, right? We normally call him 11 pi over 6, but there's a problem. This is the problem. It says we only have the ability to either go forward to pi over 2 or to go backward. So what that means is we can't go around. This is not possible. We can't go around. The most we can do is go backwards. So our answer can't be 11 pi over 6. It has to be negative pi over 6. So our answer for this is theta equals negative pi over 6. That's the only twist on this that an inverse function has as opposed to any other function. So is it really that bad? No. It's just something extra you have to remember about the range of the inverse function. Okay? So, or the domain of the inverse function. All right, let's do another one. Let's do another one, and then we'll put a nice little cute little twist at the end of it. Okay? Here we go. How about this guy? Arc, we'll write it differently. Sine inverse of let's do one that's cuter. What are my cuter? Sine inverse of 1/2, but this time we'll make it positive. Okay. Well, you do your rewrite. Draw a nice little bubble. You know this is equal to an angle. So say sine of what angle equals 1/2, and the added restriction is that theta has to be in between pi over 2 and negative pi over 2. That's all this means. So let's draw it. This guy is positive in 1 and 2. These two quadrants is 1 and 4. So where am I living? Obviously 1. So here we go. I'm going to draw my angle in 1. Here would be theta. Here's my y of 1/2. My x of root 3 over 2. So that means this guy needs to be what? Needs to be What angle is that? Pi over 6. Sorry, guys, I got sidetracked thinking about the last problem. I think I may have botched it. If I can't remember if it was root 3 over 2. I don't know, not for sure. It should have been that angle, which is pi over, whatever. If you have a question, email me. Equals pi over 6. Alright, so it's really that simple. The bottom line is you can never have an angle going through this way. It either has to go from here to here or from here to here. Alright, so it's really not all that bad. Alright, you ready to stack this a little bit? Here we go. Let's stack it. Erase. Okay, what if I said find this? First find the cosine. I want you to find the cosine of the arc sine of negative 1/2. Alright, well guys, let's go back to math 099 whatever, and let's talk about the order of operations. Order of operations says you do the innermost whatever first, right? Innermost parentheses first. So we first got to figure this out. So you go to the side and you say, okay, arc sine of negative 1/2. We'll call this theta, right? So in our mind, what do we say? We say sine of an angle equals negative 1/2. And we have to be living in between negative pi over 2 and pi over 2. So this is 1 and 4, as we've done the last couple times. Yeah, it's really easy to get into a rhythm with these. This is 3 and 4. So we're living in 4. So let me draw my triangle. Let me get an idea of where I'm at here. Here is negative 1/2 for my y. Here's root 3 over 2. Okay, what angle is this? This is 11 pi over 6 if I were to go the long way, right? But I can't go the long way. I can't go the long way. I have to go backwards. So this should be theta is negative pi over 6. So now that means that this angle here is negative pi over 6. So what does this give us? This gives us this beautiful blob of goodness that this is just saying cosine of negative pi over 6. Okay, so what's cosine of negative pi over 6? Good news. We pretty much already have the point of where negative pi over 6 lived at. Why? We drew the picture. So what does that have to be? Well, obviously the x is root 3 over 2. It's really that dang on simple. It is not hard at all. You just got to take some time and understand this added restriction that we have with sine. Now obviously when we talk about arc cosine and arc tangent, there's going to be an extra restriction to each one of these as well. Okay, so let me just go ahead and I'll jump to the chase about these two as well. Okay, tangent has the exact same restriction as sine does, so that's pretty much all there is to it. Okay, so let's look at, let me change my color back here. Let's look at arc tangent of let's say 1. Okay, so once again you start off by saying this is equal to an angle. Okay, and then you say, alright, well, tangent of what angle gives me 1, right? And he has the same restriction as sine. That's the point you need to keep on to. That tangent and sine have the same restriction. Cosine's the weirdo in this case when we're talking about inverses. He does not have the same restriction. Okay, so now when we figure this out, now you got to say to yourself, tangent's positive in 1 and 3, and this is 1 and 4. Obviously you're living in 1, so we're looking at living here. What is the theta that has a tangent of 1? Now guys, you got to start dividing, right? You got to divide. Well, the only guy where I'm going to divide the sine divided by the cosine, that's what tangent is, and I get 1, is this guy, because it's root 2 over 2, root 2 over 2. That means this is pi over 4. So that means my angle theta is pi over 4. Easy peasy lemon squeezy. See, it's not that hard. You just got to know your unit circle yet again, coming back in effect. All right, let's talk about arc cosine. Arc cosine, okay? So arc tangent, arc sine have the same added restriction. Arc cosine is a little different, and this is why. Cosine, remember, it's about catching all these outputs here from 1 to negative 1 on the cosine graph, and the cosine graph does this, right? So if we start high, right, at 0, this is at 0, and we go this way, we catch everything from 0 to 1 like how we did previously, right? So, and this happens at pi over 2. So if we go backward like we did before, the minute we go backwards, it doesn't pass a horizontal line test, right? So the idea is it has to pass this thing to make it kind of a function. So I'm going to catch all these, but I'm going to keep going forward, and this happens right here. It gets to -1 at pi. So here's the moral of the story. Arc cosine, why does it have all these additional lines on here? I have no idea. Press a little hard. Okay, so arc cosine of a number, guys, this guy is equal to an angle, but this is the added restriction. You're going to say cosine of that angle equals a number, but here's a restriction. I'll put it in a different color just so it makes be for emphatic reasons. The angle theta, he must be in between 0 and pi. This is the restriction that makes it a little different. Okay, he's the only guy that's different like this because he has to be between 0 and pi. So let's handle one with arc cosine, and then we'll do some more interesting stuff on the next video. All right, so let's erase this. Okay, well, actually maybe we could do one right here. So let's say I said arc cosine of √3/2, right? Well, first thing you do, you start off by saying this is equal to an angle. So you say cosine of what angle equals √3/2, right? Well, it turns out, ice is hush. It turns out that that in addition with this guy being in between here, right? This has happened. Cosine's positive where? 1 and 4. This guy is in between 0 and pi, where that's 1 and 2. So that means we are living in 1. Alright, so think unit circle here. Where's x √3/2 and 1/2? It turns out a lot of these angles happens to be pi over 6, which is really weird. I had to give you one that's not pi over 6. Go figure. So theta is equal to pi over 6, which means that this crap is equal to pi over 6. Very easy. Alright guys, next video I will do a little bit of combinations of all the stuff we've had in the past. Since arc cosine is really an angle, that means I can tell you to find a sum angle or a double angle formula of the arc cosine stuff. Alright, remember, in order to go somewhere and do